Okay, so what I did here is I tried to take the booklet, scan it, and put it on the smartboard so I can still give a lesson if needed. Uh, Make sure you put a comment or some feedback on Edmodo or on YouTube to tell me if this works for you or not. Otherwise, we could find something else. Um, but I'm just going to post it up here. I'm just going to go through your booklet. I'm going to go through most of what the notes say. And the focus will be the examples I'll do with you. And I'm going to just do them in order as they are in the paper. That way, if you only have a problem with one or two of the examples along the way, you can just fast forward and try and find that a little faster and easier. So let's see how this goes. So we're looking at radicals. We're looking at the first lesson, which is going to be simplifying radical expressions. Majority of this should have been a repeat from your grade 10 math lesson, so hopefully it keeps this way. It talks here in Module 4, you learned how to simplify radicals. Of course, we didn't do Module 4 yet, but again, that should have been a review of your grade 10 math. A couple things we just got to keep in mind here is the radical itself is anything with that check mark symbol. That's going to be a radical. The index is going to be the number that goes inside of there. So if it's a square root, there is an index of 2 that we just don't write. It's assumed it's there. If it's a cube root, we write the 3, the 4th root, so on and so forth. And any value underneath the radical symbol is going to be your radicand. So again, just some terminology refresher there for you. So the only one thing here is, like, I don't know about everyone, but I didn't really stretch this too hard in the grade 10 math, is going to be when we're looking at the properties of radicals. One of the ones we're going to come back to is this first property they have in our booklet, which is the inverse operations property, where you have an index of n, a to the power of n. So if n is a positive integer, it's greater than or equal to 2. Basically what we're saying here is if your index and your exponent on your base and your radicand are the same, then it's going to be just the same value of a, but it's going to be more specifically the absolute value of a. And again, my grade 10s, we didn't deal with that. The absolute value brackets just means whatever's inside of there must be a positive value. So if this is the absolute value of -3, the answer is going to be +3. And we will deal with absolute values more in an upcoming unit. The product property of radicals, of course, is the other one we did look at. This is just going to be along the lines where if you have the square root of 10 times the square root of 2, it will equal the square root of 20. We can multiply our radicals as long as they have the same index value on each. If they don't have the same index, it doesn't work. And the same thing goes with dividing. So they call it the quotient property of radicals. So again, you have a over b all under the radical sign is the same as square root of a over square root of b, or n root of a over the n root of b. Again, so that should be review as well. Here we go. So jump straight into the first example. One thing I like to do just when I'm getting back into this is I make myself a list of all my perfect squares with a PS, just to help me with shorthanding these. So my perfect square is 1 squared is 1, 2 squared is 4, 3 squared is 9, 3 is 16, 25, 36, 49, 64, my brain hurts now, 81, and 100 are my perfect squares. And what we're looking for is trying to simplify this by removing out any perfect squares that we can factor out of that value. So in this case, right, the biggest perfect square we can pull out of here is going to be 25. So this is the square root of 25 times 2. So I didn't change the value. 25 times 2 is 50. Of course, you can rewrite this as the square root of 25 times the square root of 2, which is the way I like to write that. So that's the way you'll be seeing it most frequently from me. And then we can simplify by completing this. The square root of 25 has an answer of 5 times the square root of 2. And that is a simplified radical. Same thing here. Division ones, we can work with individually top or bottom, or we can piece them all together as one, just as the situation implies. As we can see here, we have the square root of 81 over the square root of 36. These are both perfect 6. The only thing is we can leave improper fractions, but we always simplify our fractions. So these are both divisible by 3, so that becomes 3 halves, and we would leave that as our final answer. The square root of 1800. Again, so we're trying to pull our biggest square root out of this. Now, the cool thing about this is I want to break this into the square root. I know 100 is a perfect square, so 100 times the square root of 18. Now, I already knew I pulled a perfect square out of here. The thing is, if you look at the square root of 18, can I divide another perfect square out of there? And as it happens, yes, I can. I can simplify that, right? Because 9 is a factor of 18, and it is a perfect square. So we can turn this into the square root of 100 times the square root of 9 times the square root of 2. With that, then of course I can put this, well, the square root of 100 is 10 times the square root of 9, which is 3, times the square root of 2, and 10 times 3 is 30. So my final simplified radical is 30 root 2. Now that being said, because 30 was our first value here, 30 squared is 900, I could have jumped straight to square root of 900 times the square root of 2 if I recognize that 900 is a perfect square and I could factor it out of 1800. If you can recognize that, good for you. Do it up. If you don't, it's not a big deal, right? We can continue to break it down as I did the first time through that example. One thing we got to be careful of is here is this is now our index is changed. So we're seeing my index here is 3. So I'm looking for a cube root. So I need my perfect cubes to finish this one. So my perfect cubes are going to be, right, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, so on and so forth. Of course, I've gone way too big. But I need to pull perfect cubes out of here. 8 is a perfect cube. So I can turn this into the cube root of 8 times the cube root of 2. Because I can get the same index, I can remultiply and get back to the original. And the cube root of 8 does have an answer, so 2 times the cube root of 2. So that's our little refresher on simplifying some radicals. We move on to the next page here. So simplify, given that x is greater than or equal to 0, y is greater than or equal to 0. So they give us two variables, x's and y's. Of course, these have to be greater than 0, because if our radicand is a negative number, we can't find the square root of it. So they're just giving us some restrictions on the variables. Otherwise, we're doing the same thing, but now we're including variables as well. Let's go with, right, so the index here is 2, so the cube root of x squared is going to be absolute value of x, which would just equal x. Square root of x to the power of 6, of course, is going to be, right, we can simplify this into, we need to pull this, like how many perfect squares can we pull off, right? So that's x squared times x squared times x squared is the same thing as x to the power of 6. And I can pull out 1, 2, 3 perfect squares. So there's x cubed is the square root of x to the power of 6. We'll look at that again on the, if we jump ahead to example 3 real quick here, right? We can rewrite that, right? So if we remember this is an index of 2, we could also write this as, oops, not equals. We can write square root of x to the power of 6 with that index of 2 as x to the power of 6 halves, right? The index goes as the denominator, the power stays as the numerator on the exponent, and 6 halves is 3. We get the same answer. We can do the same thing here with the next one. We have an odd number like 7. So we can have x squared cube root of x to the power of 7, which is going to be, again, that's 2. So that's going to be x to the power of 7 halves, which is x to the power of 3 and 1 half. The fact that we have a half means that half has got to stay in. So x cubed square root of x. Something we will, again, look at in multiple different ways if we need to. I don't want to write this out long like every time, but just again for the first one. So I have square root. I'm going to break these into perfect squares. So x squared times x squared times x squared times x. That's 2, 4, 6, 7. And then times y squared times y squared. There's my y's. Power 4 accounted for. So I got 1, 2, 3. I got 3x squareds there. I got 3x squareds. I hope we can not catch that one. Can I erase that? Go back and edit it. 3. So that'd be x cubed. I got that's gone. That's gone. That's gone. I got the y squared and y squared. So I got 2 y's I can pull out of there. 1x left, and I have to leave that one in because it's not a perfect square, so it's got to stay under the sign. So that's the simplified radical of x to the power, square root of x to the power of 7, y to the power of 4. And of course, they got to throw in some values here, so the same thing happens. If we have a coefficient in here, we can still work the same way we did with our previous examples of simplifying the coefficient, simplifying the variable, simplifying the variable. So this is going to turn to the square root of 4 times 2 x squared is, I can leave it as such. And this is the way I like writing them, is leaving them, right, if I have an index of 2, leaving these as multiples of 2 as the exponent. And then I just kind of go through and say, okay, that has a perfect answer, that has an answer, and that has an answer. So square root of 4 is 2. Square root of x squared is just x. Square root of y to the power of 4 is y squared. Anything that's left under the radical symbol stays under the radical symbol. So 2xy squared times the square root of 2. Let's look at the next example here. Same idea. So we have square root of 25 is a perfect square, so I can leave that one be. Square root of x to the power 6, that's a perfect square, we can leave it be. And that's a perfect square, we can leave it be. So square root of 25 is 5, spoken for. Square root of x to the power of 6 is x to the power of 3, spoken for. And then the y just stays spoken for. 50x cubed y to the power of 10. Pardon me again. So again, we're looking for that biggest perfect square to simplify the coefficient first. So that's the square root of 25 times 2 times x squared times x times y to the power of 10. And again, so like I said, I can look through here. I can pull that square root of 25 out. I can pull the x squared out. I can pull the y to the power of 10 out. Because they all have answer. Square root of 25 is 5. Square root of x squared is x. Square root of y to the power of 10 is y to the power of 5. And that's left with a 2 and an x under the radical symbol. So, the one thing I do want to say with use caution with is to rewrite. If I was to rewrite this exact same thing again, and I'm not writing neatly, if it's a mess, it's going to end up coming out to like 5x y to the power of 5. Right? If you don't write that with that power carefully, it might look like an index, and we cannot mix those up. You've got to write your answer clearly, because honestly, if you write your answer in like this way, that is an incorrect answer. We didn't go from a square root to a fifth root. So you've got to be clear and concise with your answer writing to make sure we are getting things expressed clearly to the next person who has to read your work. Last one here is going to be the cube root. So again, we need to pull out cube roots, multiples of like 3, right? So cube root 28. Again, we went through my perfect square list back here. 1, 8, 27, 64 is the cube root. And of course, I can pull that out of here. So this becomes the cube root of, I'm going to make my list. I can pull 64 out of there. Times 2 is not a cube, so we can say x to the power of 14. So I need multiples of 3, right? So that's going to be 3, 6, 9, 12. And that'll leave me with an x squared behind. And again, I can work through this. Cube root of 64 is 4. Cube root of x to the power of 12 is x to the power of 4. So I can rewrite those ones in. So that's going to be 4x to the power of 4. And then I'm still left with a cube root of whatever's I couldn't pull out of there, which is the 2x squared. So that is some more in detail ones that might need a little more practice, but the learning activity, of course, will have practice for you as well. Works through the first part of this example. Simplify the following expressions. Assume that x is greater than 0, y is greater than 0. So again, I'm not going to spend too much time on this. I'm going to rush through this because we just did a more complex version of this. So this is going to be the square root of x squared times x times y squared, which is going to be x squared is x, y squared is y, and I am left with an x underneath. This is a cube root, so I need multiples of 3, so this is going to be cube root of x cubed times x, which of course is going to give me x times the cube root of x for the final answer. Expressing mixed radicals as entire radicals. If you are given a mixed radical, it is possible to rewrite it as an entire radical. This is the reverse of what we just did, so not overly complex here as well. We just got to take 4 and rewrite it as a radical, so that would be 4 squared, right? So 2, 4, 2, which is going to be 4 squared, so the square root of 16 times the square root of 3, and of course 3 times 16 is 48, so that would just be 48. Right, this would become the square root of x squared times x, which is the square root of x cubed. This is going to equal square root of x squared of 4 times x times y squared times y, and this will be back to x to the power of 5, y to the power of 3. Again, just using that pattern. I want a cube root. Again, this is going to become, I have an x, so I want a cube root of x cubed to put that x back in there, and there is an x squared already in there, and that's just going to become the cube root of x to the power of 5. Comparing and ordering. Of course, these ones are going to be, you can't compare and order if they're not in the same format. So we need to first put them in the same format, a similar format, so we can compare them. This is going to be if you don't have a calculator handy, right? Of course, we can use a calculator, get decimal approximations, and rearrange. But if we didn't have a calculator, if we said no calculators test, well, we could, in fact, still do this without a calculator. Just put everything in context of a radical. So entire radical, sorry. So 2 times the square root of 3 becomes the square root of 4 times the square root of 3. 8 is going to become the square root of 64. And the square root of 36 is our complete radical of the other one, final point. So this becomes the square root of 12, the square root of 64, and the square root of 36. Now, because they're all in complete radical form, we can just put them in order, which would be 12, 36, and 64. But we're never done there. We always have to write our final answer with the original format we were given, so I can't leave square root of 12 as square root of 12. It was given to me as 2 root 3, so I'm going to rewrite it as 2 times the square root of 3. Square root of 36 was given to me as square root of 36. It stays. The square root of 64 was in fact given to me as 8, and there's my final answer. So the same thing goes here. We can just put everything under, so at least it's square root of x, square root of x, square root of x. I can keep it that way. So that's 3 squared, square root of 9x, square root of x thing. 5 squared is 25, so the square root of 25x. And again, now everything's in x format, so that's going to be the smallest one is 1x, so the square root of x, then 9x, then the 25x, and final answer written in original form, so that's the square root of x, 3 root x, and 5 root x. This one we noticed we have a different index, 3, 2, and 4 are my indexes on that one. So instead of trying to fight, rearrange, reorder, again, like something like that, if you have a calculator, stick to using your calculator, find the decimal approximation, put them in the correct order, and it shows that in your notes. Here's some stuff to read through. We worked through some of this. Let's keep going here. Solve for x. This is going to be getting into, I hope that's what we're getting into next. We're setting up for the principal square roots here. So if we are given x squared equals a, so a value, then when we're doing this, so here if a equals 25, so if x squared equals a, they're saying a equals 25, we'll rewrite it as x squared equals 25. If we're writing it in this form, if we have a square, we're performing the square root originally given to us that x squared equals. If I go and say I want the square root of both sides, then we are responsible for saying, well, that means that x is going to equal plus or minus the square root of 25. Right? We need to tell them that. If we are given in the other form, if we are given something as a square root, basically if they give us the square root of 25 equals, again, we got to remember that they want the absolute value of whatever the base is, which means it doesn't matter what this value is. There's only one answer, and that's going to be the positive answer. So this will equal 5. That's it, that's all. So again, if they ask for the square root of a value, you're always giving them the positive answer, and that's going to be called the principal square root. This is, again, just for clarification for people in the future. So this is why we look here. Well, this one specifically says I want the negative of whatever. So how do I get the negative 5? I want the negative value of whatever the square root of 25 is. So the square root of 25 is, in fact, going to be a plus 5 value. How do I make a negative? By saying the negative of that. That becomes negative 5. Right? This is going to have to be, yes, it could be plus or minus 16, or plus or minus 4, but because they gave us the square root, we have to assume the 4, and we can say minus 4, right? And that takes a little getting used to as well, but as you use them more, it starts to make more sense, especially when you set for ease of clarification, you'll see why it happens. Which takes us to this here, and this is going to be, right, square root of 36. They gave us it's a square root of 36. So it's an absolute value, so it's got to be 6. Plus or minus the square root of 36, the fact is they told us they want both the positive and negative roots of this. So this is going to be plus 6 and minus 6, right? Plus or minus 6. This one again, this is going to be the 6, but the negative is separate outside, so the negative stays, plus 6 stays. We can still pull out that negative 6 value. The square root of negative 36. Of course, they're going to tell you in your booklet there is no answer, which is actually not true. Not something we're going to cover in grade 11 pre-cal, but just as a heads up in the future, what we could do with this is we could break this into great equals the square root of 36 times negative 1. So we can say the square root of 36 is 6 times the square root of negative 1. So we can simplify. We don't need to. And as you continue working through with math, you're going to find out that the square root of negative 1 actually has a math term for it, and we call it lowercase I. So that's going to be an answer that is 6i.
if you continue with math in the future. Nothing too complicated. It's just something that we can work with later. Two i's multiplied can cross each other out and make a 1. So it's helpful to save that value. Now, when we go to example 10, this is where it could be confusing. Again, you got to remember they want the absolute value of what's in here. So even though you're saying the square root of -2 squared, or 2, it looks like it's -2, but they want the absolute value under there. So this is still going to have an answer of 2. 3 squared, again, we're looking for the absolute value, and that'll just be 3. So if anything's going to mess you up, it's going to be this guy here. Just remember those absolute values. Even if it's negative, they give you the square root, we got to go for that principal square root, which is the absolute value. So these are some rules that we have in the book that we follow through. Take a look, right? Read through, send a question if you have any questions, but handy little set of rules to have on hand. Again, some more in your notes, stuff you can read. Hopefully this will make a little more sense as you're working through, but not necessary for us at the moment. Like I said, you can read through it. The last thing I'm going to look at is example 11. Basically what we're looking at is A is the most important one out of this. In example A, we're looking at what restrictions are going to be. Identify the values of the variables for which the radical is defined in a set of real numbers. What they're asking is for what are the restrictions? What can x be and not be? Because recall that we cannot have the square root of a negative value is a big no. So we have to make sure whatever's under here, whatever my radicand is, it has to be a positive number. And how are we going to tell people that? Well, we're going to say, well, just as a heads up, 5 minus 6 has to be greater than or equal to 0. It has to be positive. And then we can just solve for this, and we can say, well, therefore, add x to both sides, so 5 is greater than or equal to x. That's written backwards. We like our variable first. So we just flip the whole thing. So x is less than or equal to 5. So for this equation to work, to be true, right, x has to be less than or equal to 5. What happens if x is greater than 5? Well, if x becomes 6, 5 minus 6 is -1. Incorrect answer, error on your calculator. Right? But if x is less than 5, if it happens to be 2, 5 minus 2 is 3, and we can find the square root of 3. So that's what we're looking for is restrictions. That was the most complex one. All of these are otherwise like, right? Looking for restrictions here, x squared has to be greater than or equal to 0, square root of both sides, therefore x has to be greater than or equal to 0. Y to the power of 5, again, we can find the 5th root of both sides again, because it's y times y times y, just y has to be greater than or equal to 0. The only thing that's going to be something to keep an eye on here is we notice the index here is 3 and the index here is 6. Keeping in mind, we follow the same rule with odds and evens, right? Even number on an exponent will always give us an even answer. Odd number power could give us a negative. So that is the case with this one here. When we go down here, because it's an index of 6, so that's telling us that x has to be greater than or equal to 0. But because z can be a negative number, because we can have -1 times -1 times -1 will give us a negative answer. So there is no greater than 0, less than 0 restriction. So here z can just be an element of the real numbers. So any real number. And that is that. I went through as quickly as possible. I hope I didn't lose you. Again, any questions, just email through. Send me an email and I will help with what I can. Again, please let me know how you feel about how this lesson setup was. I'm still a little nervous and I'm still just talking to myself, so it feels weird. That'll break loose as we work through, but give me a heads up on if it was handy or helpful or not, or if you have future suggestions on how to do it in the future. I'd love to hear it. Thanks.